Good evening. This is my paper on peripheral vision, basically for smart glasses with head-mounted display. I wrote the paper at the end of my undergrad in collaboration with HQST as well as Deutsche Telekom. My professor belongs to both Helsinki as well as HQST. So as you know, smart glasses are becoming really popular. They're used for information visualization, medical, as well as navigation purposes or gaming. But one of the biggest problems is the limited field of view. So if you've seen the smart glasses like Google Glass, the head-mounted display is so small that you have to really look into the screen and stare all the time. So we introduce a mobile peripheral vision model which can be used on smart glasses with head-mounted displays like Google Glass, and it's an software solution, and basically we simplify multitasking using this model. So we use this model to build a navigation application for smart glasses for both indoor and outdoor scenarios. So before going into it, I just want to introduce some terminologies real quick. Angular field of view is basically measures your extent of a 360-degree circle that is visible by your human eye, and your peripheral vision, it's basically outside your central system. And why is it important is basically your peripheral vision is responsible for your night vision as well as for your motion perception. The angular field of view of Google Glass is pretty small, it's like 30 degrees, and this limited field of view, it forces the users to really focus his eye gaze towards a small screen to extract the meaningful information, and this can really create a lot of visual fatigue. Moreover, I'm not sure how many of you have seen the Google Maps interface in the Google Glass, but it's really small, and even if you're just walking or even using biking, it's really difficult to use this app. And Google Map, basically Google Glass screen, it occupies between the near periphery and the mid peripheral area. So first it blocks your peripheral vision, and secondly, if you're really putting a central gaze into the screen, then you also block your central vision. And this can create a lot of fatalities because you need your peripheral vision to know where do you have to put your step down. You need your peripheral vision to see where the obstacles located. Similarly, for the mobile devices, it really limits a lot of cognitive ability and restricts your peripheral vision, especially if you're walking. There have been a lot of pedestrian fatalities because of this. So there's been a lot of work done to try enhancing the field of view of smart glasses, especially most of them have used like LEDs on both sides of your glasses, and most of the solutions have been very hardware oriented. Some of them have tried to talk about how you can use motion perception at the peripheral area, but they have only talked about how you can use on static users. There have been a lot of work done on how you can redirect your central gaze towards the glass screen, but there have been no work on how you can actually do multitasking. There's one paper which was published in 2016 in CHI, which is very similar to our work, and our work is actually built up on top of it. The work actually talks about the 5 guidelines that you need to basically present information at the periphery. It talks about that how you should use simple shapes, colors, instead of using some composite shapes, and how shape recognition is independent of visual motion perception at the periphery, and explain in a bit what that means. But the solution that they provide is basically they put 2 smart glasses on, on both sides of your smart glass, and it's bulky. It's more of an hardware solution, and it's more for static users, whereas we try for different lighting and backgrounds for both indoors and outdoor, and it's a software solution you can deploy in pretty much any smart glasses. And we assume that the smart glasses that we are considering are located between your near peripheral area, but you can always customize it, and explain it why soon. The contribution of this paper is we provide a model which uses color and motion to display the visual cues in the peripheral area, and then we develop a high fidelity peripheral vision navigation application for both indoors and outdoor environment scenarios, and we discuss 2 cases, strabismus and colorblindness, for which our model does not really apply. I explained this already. We use limited graphical language, and we focus a lot on multitasking. So the theories, we looked into 2 basic theories. First is the color detection and the motion detection in the peripheral area. Just digging into a bit. So there are two types of cells in the human eye. The cone cells are really responsible for color, red, green, and blue. And the rod cells are really important for your motion and night detection at the periphery. That's why it's really important. So most of the red and the green cells are located in the center. Red occupies around 60 to 70%, and green around like 20%. And the blue cells are mostly at the periphery. So that's where your blue perception comes from. And so we have tried to use these three simple colors to signal information to the users. Blue because it's the highest number of cones in the periphery, red because it's the highest number of cones in the retina center, as well as green because it's high contrast with other two cones. And we have tried to use motion detection by the peripheral vision using simple shapes. And so we digged into it a lot, and we figured out that the rate threshold or velocity for visual motion perception, it increases as we go far from the central gaze. So if an object is located far from your eye, you need to throw it at a much higher speed. So basically for our case, what we've basically assumed that most of the glass screens are located between near periphery and mid periphery, but if some glass screen is located further far, then you can adjust the velocity accordingly. We built up a very simple app initially using this model because we wanted to see how you can use this model for indoors, for places like museums, for city park, because as a tourist, if I want to look into more attractions rather than just keep focusing on the screen, either mobile screen or glass screen, is really not useful. So we made up a very simple app where if the blue color blinks on the left sign to indicate a point of interest, then you basically turn left, and once the user turns left, the entire screen turns blue. We conducted a simple experiment to see how it works. And then we kind of saw that there are other applications to it, like video games, outdoor AR games, and notification. If for video games, you can show something like a red color blinking on your right, and you can show the enemy in that way. For notifications, it really depends how complex are your notification, but I'm sure you can adapt your app according to that. So based on that, we built up a demo applications. We went through a lot of iterations. What we did is for indoor application, we use indoor Wi-Fi localization method, in that sense that we basically use the Wi-Fi access points and the signal strength, and we use the best Wi-Fi access points. And to detect the particular location, we had a customized path which was around 5 to 10 minutes long, and we built up a hash map using these Wi-Fi access points. And we made sure that all the signal strength that we are using for the Wi-Fi access points are more than 90 decibels, minus 90 decibels, so means the signal strength should be good. And for outdoor, we use GPS, which is a precision of at most 5 meters. For indoors, we tested this app for both. We deployed the app on mobile as well as on the smart glasses. For outdoor, we were using Mad Gaze, which is used a lot in Hong Kong. And it's basically has a quad-core processor, which is pretty good for multi-threading activities in outdoor scenarios. So we use that. So this is like the simple app, how it looked like. If it's blue, which means the user continues to walk straight. If it's right, then the user turns right. If it's green, the user turns left. Now, as I mentioned, we are just not using only the color perception. We're using two different types of information. First, the color and the motion at the periphery to display information to the user. Before going into the experiment, so we did a lot of iterations to it. With every iterations, we actually picked 20 different users. We actually had a balanced data set of 50% males and 50% females. And most of our users were like first-time users of any smart glasses. 70% of the users had eye power, which means they were using glasses on the top of their own glass. And I guess, so what we did in this case, you'll see the navigation hint bars, which will stimulate your peripheral vision through motion. The bar movement basically covers the entire 30 degrees of your field of your Google Glass. And these hint bars, they basically blinks like 4 times for 2 seconds, which means your bar blinks at the speed of 15 degrees per second. This 15 degrees per second is well above the human threshold, which is 2.15 degree per second at 90 degree eccentricity. Eccentricity, what I mean by eccentricity is how far your object is located from your central vision. So basically it's going to blink like this. And then, as I told, because it blinks 4 times for 2 seconds, so the total peripheral stimulation is 2 seconds. And this is well above the reaction time that a human needs to rapid movement, which is at least 250 milliseconds. So same thing we turn for the left, and the cue is activated with a radius of 3 meters from each turn. Now, initially we were only doing for indoors, but we went ahead to do with outdoors because we figured out the Google Maps, which is deployed on Mad Gaze or Google Glass, it takes at least 3 seconds for it to detect your location and give you the cue. So we went ahead and used our app and compared the two of them. So to test out the demo applications, we tried to replicate a scenario in a museum for the indoors. What we did, we had a primary task, which was looking at the points of interest, and a secondary task, navigating, because we really wanted to focus on multitasking rather than on just navigation. So we had 9 points of interest around the whole 5 to 10 minutes path. And for the indoors, we had 7 pictures on the left, 7 pictures on the right, and there was always someone who was walking with the user to make sure that the user is communicating and are not just looking into the screen all the time. As well as our path for the indoors, it was really variable with variable lighting settings. It had staircases so that we are really making sure that users not looking into the screen. So points of interest for indoor was something like we put bunch of pictures of animals, fruits, some quirky stuff so that we make sure the users are more looking into the pictures than into the screen. And for outdoors, we had like point of interest, like something like that in the city walk area. So we measure like 4 metrics. 3 of them are mental demand, physical demand, and frustration level according to NASA TLX, from 0, which is low, and 10, which is high. We also measured how much time the user looked into the screen, and we took a very simple baseline of it, like low, medium, and often, and we realized it was very basic because it was more about the user perception of how much the person looked into the screen. And we basically took that time and normalized it by the total time of the experiment to just see how much the time user actually looking into the screen. And we came up with some results with that. And here the mental demand 3 means that the number of users who are choosing the mental demand 3, the number of users choosing the mental demand 4, and same like that. I think this box plot explains much better. So you can see for Google Glass indoor using our app, 75% of the users reported a mental demand of less than 5, and same for the Mad Gaze outdoor, which performed pretty good as compared to the Google Glass for Google Maps for outdoors and mobile phone for indoors. We actually had much better results for physical demand, because especially for indoors, because on staircases it's really difficult to look into the screen or stare into the small screen or Google Glass and try walking around. So we similarly did the same results for frustration level, and we got pretty okay results. We did like a simple t-test, and we figured out that there was a lot of difference between the 2 paired sample data for both indoors as well as outdoor. Basically we took the time for amount of time, looked into the screen to figure out that the users save at least 50% more time for their main activity using this peripheral vision, and most of the users agree that they really benefited from using such an app. The 2 cases we got for color blindness, we feel that you can customize the app according to what color you can see, but there's a problem with no color detection, and in that case we think the person would rely only on motion perception, and we're still seeing how we can use our app for that purpose. We're still conducting some experiments on it. And for strabismus, it was a pretty difficult task. Both the users were, for both the cases, the users were able to complete the experiment with a lot of frustration. So for strabismus, we think maybe having a hardware change, like having a glass screen on the left, would have been useful, but that requires more hardware changes. We are trying to extend our work for AR and VR. It's really popular area of interest in Hong Kong or in Asia, so we're trying to explore there. We are enhancing our model with eye tracking features, and we are expanding our panel to just see how does it perform with strabismus and colorblindness cases. I'm repeating it again in case you haven't listened through the entire presentation. And acknowledgements. Thank you so much.
Let's thank the speaker. Are there any questions? Well, I have one, because you said you were looking into expanding it into VR and AR. Yeah. So what are the concrete ideas where would you kind of have certain items to pick up in augmented reality, or how, what's the scenario you're currently considering?
Mostly games, mostly for AR games, especially because in a lot of games that you want to show there's an enemy on the side, and you want to show some, show to the user that there's something blinking. It's very nice idea to just showing through motion perception. So that's one thing we are looking into, whether you can use that way.
Nice. Any more questions?
Did you prototype it on Google Glass? Like, what was the hardware you used, and how long were these study sessions to kind of see whether it was overwhelming for them or not?
Yeah, we deployed both on MatGaze and Google Glass, so the app is actually deployed there. And most of our experiments were between 5 to 10 minutes long, and most of them were first-time users. We didn't repeat the same experiment with the same user, all the time, because we didn't want the user to know what the person is getting, what the experiment is about. And I guess, first of all, with the entire Google Glass or any smart glass, the battery lasts for 2 hours. So you cannot really run any experiment more than 2 hours. The battery will run out. So that's a limitation of on the hardware section for any smart glasses currently out there. But our experiment were mostly running max for 10 minutes. Some users maybe took more than, especially the colorblind person, completed experiment took 15 minutes to complete the experiment. But honestly, if you use any smart glass, irrespective you're using for this app or anything, even when I use it for, when I was developing the app and testing it myself, after half an hour or 40 minutes, I was completely having a headache, because that's a limitation of the smart glass, and that's what we are struggling to, I guess that's why the Google Glass faced a lot of criticism in that area.
One more question? Yes.
So, just related to this question, did you also test the standard Google Maps app, just to make sure, or just to have this control condition, whether this one is performing?
Yeah, so maybe I didn't explain it, or I spoke too fast. I'm sorry about that. But we tested out our app with the Google Maps in MatGaze. We picked MatGaze. It had a better performance than the Google Glass, but we tested out the app with the Google Maps, and the results are basically the results that I talked about are actually comparing Google Maps on the that MatGaze Glass navigation app is the Google Maps that we tested for.
You also mentioned that just talking about augmented reality, the way Google Glass works versus future augmented reality experiences, do you think the findings will hold true for augmented reality experiences if the field of view is pretty wide?
What do you mean, if the field of view is much better?
It's pretty wide, and you can have many other forms of
HoloLens or
notification, exactly.
Yeah, yeah, that's what currently, in my point of view, there's more search done in VR than AR, because AR faces a lot of limitations. But I think one problem with increasing more field of view is you will have a bulky headset. So I think maybe they're trying to solve that issue. So I guess, yeah, I mean, I'm not sure if I correctly understand your question, but if there's more field of view, then I guess AR would probably be less important than VR in that case. But also having more field of view makes your glasses bulky, so I'm not sure what direction the industry want to really take into in that sense.
Okay, let's thank the speaker.
Thank you.